I work in Munich. Before I was working in industry at a company that's now called RWE as a wind resource analyst. And I work a lot with wake models and low fidelity model, wind farm models, in particular FLORIS. And yeah, you already set the topic, so I would get started right away. Yeah, maybe I could also say that I'm not usually part of this work package, but I think since it fits inverse UQ and parameter calibration, that's sort of what I do, or a big part of my work. So I'm very happy to show you what I'm doing. Yeah, working also a lot with FLORIS. I think there are some people here that are even developers of FLORIS, so I will try to not say something wrong in case then you can correct me. But I want to start with, let's say, how this whole topic of me also started, which was in the wind tunnel of Milano. You see here that the picture of the 3 turbines that our group has built, and they are representation of real wind turbines, so they can yaw and pitch and do everything, or many things that real wind turbines can do. And what we want to have alongside these experiments is accurate representation in low fidelity models, so in FLORIS. FLORIS is a wake model package in Python that can, a suite of wake models that has a lot of wake models and also other models, and you can do optimization and wake steering and a lot of things with FLORIS. Yeah, so we want to have a accurate representation of what is going on in these experiments in FLORIS. And as you can see here, this is sort of the first shot out of the box representation when you start FLORIS in this situation here. And then we thought about how can the mismatch be decreased, although it's already pretty good what FLORIS does out of the box. And the first thing you think about is, of course, to calibrate your wake model. So that's something we did. But additionally, in this wind tunnel, we also found that, so this is the wake represented here with these black lines. Additionally, you also have, although it's a wind tunnel, quite a gradient in the inflow, where these turbines here are on a turntable that is rotating. So maybe it's rotating here clockwise, and then there would be on a diagonal. And this is how you can simulate different wind directions in this experiment. But then also the turbines move into a regime of different flow velocity, and then your FLORIS prediction doesn't match anymore. So we learned that this is a known characteristic of this tunnel, that it has this gradient in the inflow. It also has the shear is not constant, which I try to represent here by these shear profiles, which change in the downstream direction because these roughness elements are only located at the inlet, not on this turntable. And also these swirls here mean that the turbulence intensity is not homogeneous in the wind tunnel. So all of that is known, and all of that can be also incorporated into FLORIS so that you don't have this homogeneous background flow here. You can make a heterogeneous background flow in FLORIS if you want. But so all of these characteristics are also measured in an empty tunnel. So it's not something that is caused by the wakes or by the turbines. It is just a characteristic of this wind tunnel. But since the group under Carlo Botasso already published quite some work on using individual turbines as sensors, so trying from the rotor response, enabling the whole turbine to be a sensor that can sense its own inflow just from the rotor response, so vertical shear, horizontal shear, turbulence intensity. The next sort of step was to say, okay, can we use all of those turbines combined, and they move through this tunnel, to learn what is going on in this tunnel just from the turbines and not from going around with the pitot tube, and to then automatically incorporate it into our FLORIS model so that FLORIS adapts not only the wake calibration, but also to this heterogeneous flow in the tunnel. And this was sort of the kickoff for this way of thinking or project of soft code framework that we built then around FLORIS. Doesn't need to be FLORIS, can be also a different model. In our case, it was just that. And then we took that to the real world, which is here. And so the next step is this Google Earth picture of a real wind farm. And here you could have not exactly the same, but analogous problems. You could also have a gradient or profile in your inflow. You could also have different shear depending on the forest, depending on the roughness of your wind farm. You could also have different turbulence intensity. And based on the terrain, this shear inflow is probably, that's a difference to the wind tunnel, not constant throughout the farm. If the wind would come from the right to the left now, it would probably change here where these hills are. So there we adapted it from just looking at the heterogeneous inflow, which is maybe a good first step, to a fully two-dimensional heterogeneous flow, which we were seeking. So here you see a FLORIS picture, you see the wakes, but you see also that the background flow, which you have this commonly you split it into wake flow and background flow. And for us, the terrain induced changes are part of the background flow. So here we changed the background flow of this site. And this is exactly this site you see here in the picture. So this is a bit the introduction of what I do. Additionally, you could also have, that's also something you don't have in the wind tunnel. Additionally, you could also have a change in wind direction on the farm. If the farm is large enough, maybe this is represented by these arrows here. Here in this part of the farm, the wind has a slightly different component in the direction than on the southern end of the farm. And this is also something that you can incorporate into FLORIS if you want. So basically, heterogeneous flow is the big topic for us. It's something that we are trying to identify, and you will see more of that in the rest of this talk. One other reason, except from surface and terrain, could be also global farm effects. If you have maybe more turbines, then the presence of the turbines itself could trigger some different or some deviation from a homogeneous flow field. So I don't really usually call it inverse UQ. Usually I talk about identification of correction parameters, but I think it's similar topics. What I do is, or what we do is, we take an engineering baseline flow model. Can be FLORIS, can be another one. I think there's also PyWake, or you can write your own in MATLAB. Just the important thing is that it should be a physical base model. So you have a physical first shot. We don't want to have a black box model. And then, first of all, we calibrate the phenomena that are modeled in the baseline model. So in our case, that's for sure the wake. So wake velocity deficit, wake turbulence, and also the wake combination is already taken care of by FLORIS, and there are very many research in wake models. So we believe those are already very good. So we calibrate those. This is called, in our language, tuning. And then on top of that, we try to identify a phenomena that is maybe not modeled yet, and then we just parameterize it, and we also identify the parameters, the correction parameters. And this is what we refer to as learning. And in this talk, this is clearly this heterogeneous background flow I was already talking about. So in this sense, we have a baseline model, we calibrate it, but on top of that, we also see which part we think is not yet part of this baseline model, but it's important. And then we additionally do this data-driven correction for that part. And this is, in our opinion, a very good idea, because if you don't do that, then you will likely have in the calibration, you will start to compensate, or you may compensate for things that shouldn't be part of the maybe of the wake velocity deficit calibration, but they are more effect of the hill that this turbine is just standing on. So this is the let's say additional step we do on top of the calibration, and we refer just internally to this as tuning and learning to keep it a little bit separate. And all of this we believe must be identified then simultaneously, because otherwise if you do one of them first, then you will likely already have this overcompensation in there. And that's why we call this simultaneous tuning and learning method. If we now would have tomorrow start to use a global farm effect model, and I think there are already first models available, then this this effect here would move to the tuning, to the simple calibration, to a matter of calibration, and we could focus on maybe just identifying terrain roughness effects. I should say that these two are in fact here listed because FLORIS, you can put a heterogeneous flow field, but FLORIS sort of leaves it to you how that heterogeneous flow field actually came to be. So FLORIS does not, at least to my knowledge, have a terrain flow solver or something of that sort. So you need to somehow figure out what is the effect of hills and valleys yourself, and that is exactly what we are doing. So maybe to be a bit more concrete how all of this correction is done, if we look at this idealized wake here, then as I said, the wake is already, we are at the moment perfectly happy with all of the wake models that are in FLORIS. Before, in a previous work, there was no secondary steering model in FLORIS, and that was then taken care of by this number 3 here, data-driven correction. But now it's in FLORIS, so we don't have to worry about that anymore. So that is already included in FLORIS, and we simply now we calibrate, for example, the wake expansion coefficient by adding this P always, these are our correction parameters, by adding a correction to the literature value. And then these dots here are the way how we parameterize the heterogeneous background flow by simply adding these what we call flow correction nodes onto the farm layout, and they take a value between 0 and 1, and that value represents the speed up of the background flow. And then we simply interpolate between the adjacent flow nodes. So in this case here, you would have a background flow that is homogeneous, and in this case, it could be a background flow that has a gradient and is increasing towards this lower left corner because this node has a higher value. And we could also replace this U. So in this case, it stands for heterogeneous wind speed distribution. We could also say it's a heterogeneous wind direction or a heterogeneous turbulence field. This can be all represented by this node concept, and these nodes can be identified. It's just a matter of if you actually have a data set where you could observe different turbulences, for example. And then the final full flow field is for us, and our nomenclature here is comprised, so everything here is comprised of a base flow, which is the homogeneous side average flow. So for example, 8 meters per second everywhere. Plus, this is the heterogeneous correction. So this shades of gray here. Plus what the wake does. So the velocity deficit in this case. So what is here? And Again, I could also replace this now with the symbol for wind direction or turbulence intensity. Then I would have a base turbulence intensity, a turbulence intensity correction caused by maybe the roughness, and a turbulence intensity correction caused by the wake induced turbulence intensity. And this ends up in a set of a lot of correction or tuning parameters, P, which is a long vector, which is stacked here by the different kinds of corrections we do. So we have the wake, all the wake model parameters that we want to calibrate, and all the flow tuning nodes and all the turbulence intensity tuning nodes. And as I said, this whole vector needs now to be identified at the same time simultaneously. So just the conventional calibration together with the additional data-driven sort of model agnostic correction. As training data for the wind tunnel, we can use this detailed rotor observer data, which actually doesn't tell us just the power of the turbine, but also the shear, as I said, and the rotor can sense the turbine's intensity. So in the wind tunnel, we can do a little bit more identification than in the real world, where we, at the moment at least, just have power production SCADA data for conventional wind farm that is just the normal data that everybody knows. So actually in the real world, we specialize at the moment on identifying heterogeneous wind speed fields and not heterogeneous turbulence intensity distributions, for example. So we just reduce a little bit these possibilities that we have and specialize here on the finding heterogeneous flow distribution on a wind farm. We do this by a maximum likelihood estimation that should give the most likely combination of parameters for the given set of SCADA observations. However, and I think maybe this is the interesting part for your work package, this is quite a lot of parameters or degrees of freedom we have now. In some cases, we have over 100 or 200 of these correction parameters, or only for the wake model, you have already 10 or more that you could tune. And a lot of these might be correlated or achieve similar effects on the power of the turbines, while others are completely unobservable or have no effect. So these problems likely ill-posed and might not converge very well. That's why there's an intermediate step, and this whole estimation is supported by singular value decomposition, where basically what is done is these parameters are rotated based on their sensitivity towards the output into a set of orthogonal parameters, which have now the trait that they are uncorrelated, so they don't influence each other's sensitivity on the result. They also are not physical parameters anymore, so they're a bit hard to interpret, but it can be done, as we'll see later on. Plus, the SVD will also give you a measure of observability of each of these parameters, which then enables us to say, okay, we have an observability threshold, and if the observability is under that threshold, we don't even use those parameters anymore. So of those 100, let's say we have 100 orthogonal parameters, 100 physical parameters, then we would get 100 orthogonal parameters. But of those, 30 actually don't matter really for the result, and they're not observable. So we can discard them, which makes the identification process run even better, while the final result is just as good as if we would keep them in the identification. Good. I'm going to go to the results. I'm seeing that I'm burning a lot of time, so I'm speeding up a little bit. This is the result for the background flow for the onshore farm I just showed you, and maybe we just focus on these subplots down here. where on the left one we see the identified background flow. These red dots are these flow correction nodes that I showed you before. And the right picture doesn't have these correction nodes because the right picture is just a CFD simulation without turbines. So it's just a terrain simulation. And in our case, in the left case, it's from this full this data-driven identification with the turbine production data. And we, in this case here, just want to compare qualitatively how these two compare. And in fact, I mean, I'm showing you the best one now, but the others are also looking quite good. They seem to match quite well. So you see here that you have speed up regions in the this color here represents speed up factor. You have speed up regions in the CFD simulation, and you also have quite a matching parts in the data-driven identification. And the speed up regions in the CFD simulation are just the regions where there are hills, and the slowdown regions are regions where there are valleys. So in this onshore case here, case 1, we are quite confident that these corrections here actually represent orographic features and speedups induced by the terrain. And of course, if you run now the FLORIS model with this background flow instead of this homogeneous one I showed in the very first slide, then the result is a lot better. It's also better than the CFD simulation, but that's expected since the CFD simulation was not run with any knowledge about production data. Then now going back for a second to this SVD and highlighting another point is that this SVD also has the advantage that you can actually look at this rotation or this eigenvector decomposition that is that emerges, and you can then understand a little bit the couplings and the correlations of your problem, and also what are the most important parameters in your problem to reduce the error. And one visual thing you can do is you can show the individual columns of the rotation matrix, or one which represents sort of modes of the background flow. So one plot here shows you what one orthogonal parameter tunes. So before, one physical parameter was tuning here the value at the physical point here and changing it, the speed up value. Now this orthogonal parameter is instead responsible in tuning this combination of points, which is this whole mode, which apparently makes the south-north divide in the background flow. And then when you go to higher orders of these modes, you see that they start to tune. These are the most important ones I show here to you. More and more fragmented features of this seem to be important for reducing the error. For example, if you look here in the north, you see that there's this sort of divide here. And when you go back to the picture, you see that this is in case slow velocity here, high velocity here. This is not probably not caused by waves, because the inflow direction is something like that. But in fact, if you look at the map or if you look at the CFD simulation, you see that there's a sort of valley between those two rows of turbines. And almost done going, but before showing you the second results we have for the offshore farm Anholt, there we were looking for the second aspect, global farm effects. I put a question mark here since I think it's much debated topic, and you have different names for these effects: global blockage, edge effects, or deep array effects. What is for sure that this farm has a much higher turbine count than the other farms. So, and it's also flat. So if wake effects or if these effects emerge, then we would maybe see it here. because you have lots of rows and lots of wake interaction. Verification is difficult. And one thing we did is we split the data set into, or we performed one identification where we used only SCADA data under stable conditions, and we performed another that only used data from unstable conditions, because these two atmospheric state, or at least in the stable conditions, you would expect much more of these farm effects. Looking at the result, here always comparing the result for unstable and stable conditions in each of those subplot pairs. And the little arrow here shows you the direction. And I only took here, I'm showing here only directions where the farm is coming either from the south through the whole farm to the north, or from the north through the whole farm to the south. And what you see is that clearly in most of the stable cases, at least in most of them, you have, first of all, higher tuning towards, or deceleration towards the trailing edge of the farm, also here. And you also have more of these seem to be accelerations at the edge of the farm. Also, you see it here. Then in the corresponding identification that was performed with using only unstable SCADA data, or SCADA data from unstable conditions. So that's at least a qualitative comparison. What is really going on here in the last sense of the ground truth is hard to say. I think it's a good indication of that there are these kind of effects. It could be also problems in the wake combination model. I think it's very likely because these are just empirical models, and also they are not part of our tuning at the moment. If there were, if we somehow would tune the wake combination model, which would be maybe an interesting future task, or we would use a different one that is easier to be tuned, then I'm sure that in the singular value decomposition, you would see a coupling between or you would see an eigenmode, which shows you the trailing edge of the farm, and also shows you that this is coupled with the wake combination model, because there in the trailing edge, you have the most wake combinations. This was not done in the present case because we wanted to use the models that are currently available, and we already had a lot of degrees of freedom. Maybe that's a next step to do. It definitely shows that that you can improve your match quite a bit with these corrections that are made here. And this is my last slide, so I'm gonna cut it down because I think I talk a bit too long. So I'm working on a hybrid approach, not want to do a black box model, but data-driven corrections on top of physical submodels. The SVD support is something that, at least for me or for us, worked very well. You can assign this observability. You have the orthogonal parameters, which you can try to interpret a little bit with these eigenshapes. And next steps are, for example, looking at the most recent generation of models like blockage or farm effect models, and then looking at the couplings and the result we get. But this is it. Yes. So thank you very much for your attention. And if there are any questions, I don't know if we still have time. I think I went a bit too long, but if there are, I'm happy to answer them.
Yeah, thanks a lot, Robert. That was really interesting. And no problem about the time. We have time for questions. So
okay.
I see, somebody raised their hand. So yeah, if you have a question, please raise your hand. Also, there's a question in the chat from Benedict. So I'll just read it, but yeah. So the question is, after the calibration, what is the computational effort of the resulting FLORIS model? Are you able to run it in real time during your tests so that you can reconstruct the wind situation in the wind farm parallel to runtime? Or is the resulting model mainly suitable for the reconstruction of previously recorded measurement data?
Yes, so I can say a bit about the computational efforts. So this was all done with the previous FLORIS version. I think now, just recently, the newest one was released. After the calibration is done, it runs very fast. So even in the offshore wind farm, you get the result in under a second. So it's not very computationally heavy. What is very heavy is the identification. And in the Anholt case, this was really a restricting factor. So we couldn't, for example, this identification where it said we did it once for stable, once for unstable conditions. One reason for that was also that my computer cannot just handle doing both simultaneously. So while it was convenient, we did it separately. But I think with the newest FLORIS version, it's a lot faster with large wind farms. In the previous version, it was still struggling with 111 turbines.
All right, thank you. Great, and now, yeah, question from Matthias.
Yeah, very interesting work. In particular, when you pick out Anholt, which is our farm in Ørsted, so I'm always happy to see that analyzed. But we did some analysis back way back of this very wind farm to look at some of these effects, these gradients. You know, they have many names, and we did some LiDAR analysis. So I'm a bit sad to see that the direction that you didn't include was when you have the western direction, because that was the most analyzed direction. And I remember that we saw a general gradient, so getting faster speeds when you went to the north, because you had, you know, the wind had further distance out to out over ocean, so you know, less surface.
Yes, you bring that up. That's actually good because I cut that out of my presentation. No, we also analyzed this direction, and where you have this land-induced gradient, yeah, and this is also picked up by the data-driven correction. So we compared that to one from Worf, I think, from a paper from Alfredo Peña, and yeah, this also worked. So this gradient by this peninsula can be also picked up.
Okay, I'm happy to hear that.
So it seems to exist, yeah.
But if I may jump in, sorry, this is Carlo. For us, that's an easy solution because the wind from the west, the farm is thin, so you don't have so many rows. So it's more interesting to look at the north-south, where you have many rows, and so you have more of these deep array effects. So that's why we concentrated on this in the presentation.
Another quick question: have you tried to compare it with the mesoscale data? Because we found a couple of times that there's pretty good match between these gradients and the mesoscale data.
Yes, exactly. This is unfortunately I excluded it, but this exactly the slide I would have shown, and it's in the paper that we will submit very soon. So it's the comparison to the mesoscale data looks very good. Although in the mesoscale model, I guess you don't have the wind farm. I don't know if you have parameterized. So the mesoscale simulation doesn't know that there's a wind farm, whereas in this one you have included also any effect from the wind farm onto the atmosphere. So that's a difference then in the result.
Yeah.
Eric, your microphone is muted.
Thanks. Question from Michael Howland.
Yeah, great. Thanks so much. Very interesting talk. Very nice to learn about. So yeah, I was curious if your parameter calibration is sensitive to the form of the unmodeled phenomena that you're incorporating. So if you change the form of these unmodeled phenomena, which you're also learning parameters of, does that actually change the resulting values of the physical phenomena in the original FLORIS model? Let's say if you change the form of this unmodeled phenomena, would it change the calibrated result of your wake spreading rate in FLORIS, for example?
So you mean, for example, if I change the mesh spacing, if I make a very fine mesh or a very large mesh, would that give a different wake model calibration?
Right. Maybe, yeah, perhaps. Yeah, I got bogged down going quickly through it. Yeah, so yeah, from how I understand your four-step process, you have parameters that are incorporated in the original FLORIS model, and then you add additional terms which are learning unresolved physics, which is not included in the original FLORIS model. And you have to assume some form of that unresolved physics.
Yeah.
And then that introduces itself additional parameters. And so I'm curious is if you change the form of that unresolved physics, would that actually change the resulting calibration of your physical parameters that are already baked into the FLORIS model?
Yeah, I think the singular value decomposition doesn't save you from identifying things that are not true. So you, I would never say this is we identified the ground truth just because we use this singular value decomposition, because it will throw out everything that's not observable. And I did a sort of forward uncertainty quantification or sensitivity analysis by using different mesh sizes. There was pretty robust. But also when you change the, for example, when you change the ambient input condition, the learning conditions, then your result also changes. So I would say, yes, probably it will have an effect on the final wake calibration. You cannot entirely prevent that. Also, if you formulate it in a different way, that we didn't do that yet. Maybe that's an interesting point to follow up.
Yeah, I think it's really fantastic work. I mean, I think I agree with your idea to learn all of the parameters at the same time. This enables the nice SVD method that you're using, but I am wondering how that also affects the calibration of the original parameters in FLORIS. So I think it's an interesting point to think about.
Mm-hmm.
All right. Excellent. And there's a question from Stoyan.
Yes, thank you. So Robert, thank you so much for this very, very interesting presentation. I really liked it. I wonder now in your Anholt results, were you optimizing the grid, so the mesh velocities together with the wake model parameters in one shot? And if so, did you somehow kept the wake model parameters the same when optimizing for different wind directions? Or how did you do that? Or did you just re-optimize everything again when changing the wind direction? How did you tackle that? And I guess that would also relate a little bit to questions related to the well-postedness of the optimization problem. But that's a separate question. Maybe I can ask after that. But if you just first try to ask answer the first question.
Okay, so these flow corrections, I showed this in the presentation. They are, let's say, they are different for different directions. Obviously, when you come from the south or from the north, then always this low speed region is on the trailing edge. But the wake corrections are just global for the entire problem or the entire identification you do. So ideally, and I had to look it up, I don't know it for certain at the moment, for this stable and for the unstable identification, these were two separate things. We would get the same result for the wake model calibration, since that shouldn't depend really on the stability, or I'm not sure, but it should be fairly similar. And I think this was sort of the case. So that wake tuning in that case at least was robust. I don't know if I answered your question.
Yeah, just to for me, so basically you were saying when taking the stable data only, you would take data from different wind directions. You would put all data in one optimization problem, keeping wake model parameters the same, and just
they were found or calibrated at the same time with the rest.
Yes, but I mean, making, let me put it another way. So the wake model parameters would not depend on the wind direction. So they are wind direction independent in the optimization. What probably does depend on the wind direction are the velocities on the mesh.
Yes.
Okay. And so you end up in a probably well-posed problem in this case or not. Okay. Yeah, so I was, that was actually, well, actually that answers actually my second question. That was related to the well-postedness. I was actually trying to kind of suggest, but I understand now you're doing that, to take different wind directions in the optimization to try to cope with the well-postedness. But you are doing that obviously already. Thank you again. It was very interesting.
Thank you. Yeah, the part with the wind direction you now understood yourself, but I actually went over that pretty quickly. So yeah, these meshes that we put on the farm are basically meshes that represent different wind direction, or they're identified for different wind directions. Yeah. So you're right about that.
Thanks.
All right. Do we have any last questions?
Robert, I think the point of CANF was really the fact that the wake parameters are the same no matter the wind direction. So everything, all wind directions are simultaneously identified together with one single set of wake parameters. So the only distinction is stable, unstable.
Yes, indeed. And in my opinion, that would actually improve the well-postedness of the optimization problem, because you could take data from different wind directions and you have some of the parameters that are independent on that. Others will depend on that, but I think the number of parameters will increase maybe less fast than the number of data points. So I don't know whether you understand me, but I expect that it would be better or easier to identify the parameters when you add data from more wind directions.
Yes, I agree totally. But it's not only due to well-postedness, it's also due to the physics of the problem. I mean, I think the wake recovery shouldn't depend on the wind direction, unless you have some strong terrain effects or something. I mean, so it's more correct from a physical point of view to, again, have one single set of parameters, no matter the wind direction, at least in this condition.
Yes, yeah. Well,
otherwise it would be sort of overfitting, right?
Yes. Yeah, exactly. So my point was more like if you would just take one wind direction in the optimization and you have somewhere for a wind turbine which is in a wake of another wind turbine, you have some inaccuracy, so the model prediction is not accurate. So you could either change the wake parameters of the turbine in front of it, or you could change the the wind velocity of the grid. Yeah. So there are two parameters that would probably have the same effect, and that's not a well-posed problem. But if you would take not only this wind direction but also another one, then this well-postedness kind of disappears in some sense.
Absolutely. Yes.
Yeah. Thanks again. Very, very interesting work.
I think now I understand your point. So I think what is another point is that I think also that the irregular layouts, they are better for identification because you have much more different wake interactions than maybe a regular layout.
Yeah.
All right. I just had one quick question, Robert. So kind of connecting this to the inverse UQ topic, I'm new to inverse UQ, but I think of it as estimating a parameter value, but also quantifying the uncertainty in that parameter value. And so with your parameter estimation method, are you able to quantify the uncertainty, like put a probabilistic description of those parameters?
Yes. So one thing we can do is we can show you the uncertainty of these orthogonal parameters right away, because those come out of the SVD deconstruction and they are used for this discarding of 1/3 of them. And the other thing I did was doing this forward uncertainty quantification. So I then changed slightly, I think, the conditions, and then I saw how much the identified parameters in the end vary. So this forward quantification can be also done, although you have to reduce a little bit your problem size, because you need to. Yeah, I was doing just a simple Monte Carlo approach when I did it.
Okay, that's interesting. So yeah, kind of a combination of parameter tuning and sensitivity analysis there. All right, well, if there are no more questions, then yeah, thank you so much once again. Really interesting talk.
You have a nice working group here. Yeah, thank you.